As you know, the title of our paper poses a question. In this case, the answer is typically no. To be more precise, we find that the reported results are 40% too optimistic on average. Virtually all prior work only considers non-adaptive attacks, which led to these overly optimistic robustness values. We designed adaptive attacks for 7 of the most popular defenses, spanning the entire spectrum of defense strategies. We also provide our best practices for the evaluation of future defenses. Although this cannot replace a proper adaptive evaluation, our collection of perturbed adjacency matrices forms a black box unit test that every robust defense must pass. My name is Geisler, and I will present our work, Are Defenses for Graph Neural Networks Robust? At this point, I also want to thank my amazing co-authors. Let us now understand why the evaluation practices are flawed. Adversarial robustness is about a phenomenon that we can often find a slightly perturbed input for which the model changes its prediction. Finding these examples for structure perturbations on GNNs relate to a maximization problem where we are allowed to add or remove a small number of edges. However, this is not how defenses for GNNs are actually evaluated. Instead, prior work typically relies on a small set of approximate attacks applied to GCN or linearized GCN. Then, the perturbed adjacency matrices are transferred to the defense model. In other words, the attack is not able to adapt to the evaluated model. Hence, we call such transfer attacks also non-adaptive. While I refer to our paper for full guidance, I quickly want to illustrate how an adaptive attack might look like. Here we consider a special class of defenses that effectively disallow certain connections. This captures the popular defenses Jacquard GCN that filters edges based on feature dissimilarity, or SVD GCN that uses a low-rank approximation of the adjacency matrix. If the defense is differentiable, we do not have to do much more than attacking the defense directly with a gradient-based attack. Alternatively, we can mask out some possible perturbations during the attack. This avoids perturbing edges that are being ignored anyways. The principle is also helpful to make attacks adaptive that do not backpropagate the gradient through the model. Here we show the accuracy after an attack on Cora. We see that all defenses show considerable robustness gains if the perturbed adjacency matrix is transferred from a GCN or linearized GCN. We consider the most important threat models, including poisoning and evasion, as well as global and local attacks. The picture changes entirely if also considering adaptive attacks. All evaluated defenses have reported too optimistic robustness values. Moreover, the differences to an undefended GCN shrink significantly. In some cases, the defenses might even harm robustness. After all, the main takeaway is that every work for defenses on GNNs should also evaluate against adaptive attacks to reveal a more realistic notion of robustness. Since we evaluated many models with different defense mechanisms and with multiple attacks, we have gathered a significant collection of perturbed adjacency matrices. We will provide a set of perturbed adjacency matrices that can be transferred to new defenses. While I cannot stress enough that this does not replace adaptive attacks, it can give a first, rather cheap and standardized impression on the robustness of a model. If a defense does not even pass this test, then you already know it's not robust. So let me recap. We strongly encourage you to use adaptive attacks for your GNN defense. We also provide a robustness unit test for a first glimpse on a model's robustness. Check out our paper for practical advice on how to design strong adaptive attacks and many interesting insights into how adaptive attacks behave for different models. Thank you for your attention.